My name is Abhimanyu, and a bit about me. I work at Sajid AI Factory in Europe, and my talk is about reducing hallucinations in ChatGPT-like systems. So, um, I hope everyone is aware about is somehow interested in LLMs, and this talk is mostly about since this talk is mostly about hallucinations. There are multiple ways of reducing hallucination, and I'm gonna now deep dive into the agenda of the talk. So give you an overview. So there are as I said, there are multiple ways of reducing hallucination, and the way that I am exploring is basically using knowledge graphs. So later in the second half of this talk, we will actually dive in a bunch of code examples, and there's a good mix of code and theory in the entire talk. Moving to hallucinations. Okay. What is hallucination? So basically, large language models, as we know, is prone to producing or generating content that is incorrect, nonsensical, and not real. What do I mean by that is when you ask a prompt to a large language model, it can produce incorrect answers or responses. There are broadly two types of errors which we see. One is factual errors, but what I mean by factual errors is a model generate incorrect information about real world facts. So, for example, the moon revolves around, or maybe like the Earth revolves around moon. So that's an incorrect fact. The second one is a inconsistent responses. The model provides contradictory or conflicting answers to the same prompt. For example, you prompt an LLM multiple times, and it always produces different answers. And most of those answers could be conflicting, or some of them are conflicting, and they could be contradictory to each other. So these are mostly the two broad type of errors that we see with LLMs and why they hallucinate. The next is basically digging into why. So why do LLMs hallucinate? So LLMs hallucinate. Broadly, it can be divided into like three factors. So the first one is temperature. So temperature is basically it's a internal factor of internal parameter of an LLM. So basically, like if the temperature of an LLM, it's a parameter that you can tune. So if the temperature is low, you can generate grounded responses, which are less creative. If you increase the temperature, it could basically generate more creative responses, and which are factually incorrect, right? This reminds me of June 2023, where US judge sanctioned two lawyers for using LLMs that generated a legal brief containing fabricated case citation. So temperature is a very important factor which leads to grounded responses. Second big why is missing information. So basically, like LLMs are trained on massive data sets, which can take months or years to compile. And uh, this this can uh, this can lead to knowledge gaps. For example, something that is not present in the LLM, let's say an LLM was trained in 2022, it might not know about the events that happened in 2023. So the LLM doesn't really know about the information that happened after the training. So when you ask a question to a system like ChatGPT, since it is not aware, it mostly generates hallucinated answers, or not or incorrect answers. The third big why is the model complexity. So uh, Now, what is model complexity? Model complexity is basically like uh, training training on incorrect information. Like, for example, you have some misleading information, since there's a lot of information on the internet, mostly on social media, Reddit, Facebook, and imagine that information is used in the training, and the model actually learns around that misleading information. Now, these LLMs are extremely complex. Like, you cannot debug these are like black box. So the answers generated by these LLMs could be inaccurate by design, and it's really hard to go back and fix, or to know how an LLM is driving is coming to the response, uh, because these are opaque in nature, right? The next, so once we know like why these LLMs hallucinate, now we want to know how can we fix this problem of hallucination, uh, uh, which leads to us the methods of fixing hallucination. There are broadly like four methods. The most popular one, which you already know, is prompt engineering. Prompt engineering is basically like you write prompts, and the prompts will query an LLM, and it will generate your response. So it's usually like how good your answer is as good as your question. So if your answer has more context, and if it has a good structure, it's going to produce a good answer. So by writing or refining prompts, the developers can improve the performance of existing models without kind of like retraining them. The next one is in context learning. We will see code example of this, but in context learning is generally like uh, using examples while prompting in order to like generate accurate responses to your um, to your to your uh, to your prompts or to your questions. uh, Third one is fine tuning. I'm not really a big fan of fine tuning because it takes a lot of compute. It's expensive, and it's not feasible for everyone. So fine tuning is basically like if you have a small set of database which is very niche, something that is like, for example, you're training a general LLM to be good at maths. So you have your mathematical database or data set, and you further train the existing LLM or fine tune it on that specific data set, which is our third method. The last one, and the one that's we're going to explore the most in this talk, is grounding. So basically, grounding is like you have your LLM, and you have your real-time API source, or your database, or your data lake, or warehouse, could be anything, any source of data, and you basically hook up your LLM to the data source, so that before producing the result, it kind of like looks into the data store and tries to find relevant information if the LLM doesn't really have it. And this also help us to provide more factual and correct responses. This, as you guys have seen, this technique also leads to RAG, which is mostly popular as retrieval augmented generation. Okay, so now since we have spoken about RAG, and which is what we're going to explore in this talk, um, so LLM without data is more like a handicapped person who doesn't really know how to walk without crutches. And the favorite crutches here, my favorite crutches for LLM here is knowledge graphs. So basically, we will now dive into what knowledge graph is, and how can we use or utilize knowledge graphs to improve the groundedness of, of, of our responses, and improve the responses generated by large language models. So what is a knowledge graph? knowledge graph is basically like a semantic network that represent real entities, which is objects, events, situation, concepts, um, and illustrates kind of like relations between them. How are these things related to each other? And uh, a knowledge graph is made up of mostly three components. So a knowledge graph is made up of nodes, edges, and labels. Like most of the guys who are from mathematical background, they already know what a graph is. So a graph is basically a structure or a data structure which has node, edges, labels. Every node is connected. Every node is connected with other node with the edge, and it can be labeled. It could have a unidirectional relation, it could have a bidirectional relation, it could have a circular relation with each other. And these nodes or these knowledge graphs um, can can be like uh, can be a representation of anything. Could be a representation of an object, could be a representation of a place, could be a representation of anything that we see around. It could be a representation of a city. It could be a representation of literally anything, a bookstore or anything. To understand more about knowledge graph, how they are made, we have to look at something called ontologies. And to understand ontologies, before that, we need to understand what taxonomy is. So taxonomy is basically like a tree structure or a tree data set, which is basically like if you visualize, let's say a human is the root node, and then it branches into men and women, and then a person, George, is connected to men node, and George is by default uh, it belongs to the category human. So taxonomy, in a literal sense, is literally a tree structure uh, and the representation of it. Now, ontology is more advanced taxonomies. So basically, when you say taxonomy is a tree, ontology is like more like a graph. So a man could have some connection with a woman. So a man cannot be a woman, or a woman cannot be a man at the same time. So there's more relation between the entities. So, and that is way more powerful. That is way more powerful than what a taxonomy is, because it understands more about uh, the structure. Okay, and now putting everything together, a knowledge graph is basically a graph database and ontology. So an ontology merged with graph database becomes a knowledge graph. In easy words, you can say knowledge graphs are a combination of graph database and ontologies, literally uh, a tripled store based graph database and ontology. Now that we understand a bit about knowledge graph, what knowledge graph is, we will dive into how can knowledge graphs help us reduce hallucinations in LLMs. So there are broadly four ways which we could use, which how we can use knowledge graphs to reduce hallucinations. First is provide factual grounding. When you have a knowledge graph, it it has more structural representation of facts. For example, you have a knowledge graph about movies, so the it has more understanding of how the actor is related to one movie, and one movie is related to what director, and one director could have multiple movies. So there's there's always more structural information about the entire data. So in a way, so we can use knowledge graphs to help LLMs align with the responses and generate more factually correct answers. The next one is improving reasoning capabilities. So by understanding relationships between entities, knowledge graphs can enhance LLMs abilities to draw logical conclusions. Um, like, for example, let's say taking back the example of man and women, if it understands the relation between a man and women, it can reason about it. And knowledge graph is a really powerful tool which can actually reason about your queries. So we will look into this thing later as well. The next one is enhancing retrieval. Uh, it's basically allowing LLM to find relevant information more efficiently, and avoiding generating responses based on limited context or incorrect context. So it's literally appending some knowledge to the LLM, which is how we do it in RAG, to enhance the retrieval. Next is reducing over reliance on statistical patterns. So while we train LLMs, these LLMs are a very hard fit. So what I mean by that is these LLMs are over reliant on statistical patterns. So when you train an LLM, it has learned the structure of numbers. So basically, it knows that how one embedding is related, how one keyword is related to another keyword, and it draws conclusion from the numerical representation of those words. Um, and it overfits, so it kind of like 2 plus 2 is 4. So it always kind of know that it is more packed towards statistical pattern, and which it has learned in the training data set. So it's really hard to break it free from that the training part, which it learned during the statistical pattern which it learned during the training part. And then it's another reason it can lead to hallucinations. Now, the next is basically, now we know that how theoretically we can reduce hallucination with knowledge graphs. You can use like a RAG, you can use the structural understanding of knowledge graph, or do a bunch of these things. Let's put it to action, which is and before again looking at an example of it, I would like to discuss about why knowledge graph again. So knowledge graph, as you can see in the left picture, they are really good at representing they are really good at symbolic representation. For example, we have an apple, and an apple has a color, flavor, variety, and other bunch of things. And you can build a map of this apple and represent it in a graph form. Now, this is a very rich representation. That's how we humans derive information. Like, we build a graph and we connect those things in graph, and everything we understand is in a graph format. So I know this guy by this relation, and I have this relation with this guy. So it's literally how we humans represent information in our brain. Now, but LLMs don't really work like that. LLMs rely on numerical representations, which is also like embeddings. Um, and by providing it a structural representation and a numerical representation, LLMs can eventually produce more grounded responses. So like for instance here, uh, um, yeah, this entire representation can help LLM to kind of reason about the entire response in a more humane way. Uh, Also, the next why of why should we use knowledge graph is in the right picture, as you can see. So with this picture is taken from like a knowledge graph conference 23, and it's a very interesting thing that I came across. While you compare the retrieval speed of different systems that we have in around us, So, for example, ChatGPT has a retrieval speed with all the GPUs and all the infrastructure. It takes 5 seconds to generate a response. For Google, with all the infrastructure and all the massive compute they have, Google takes 0.56 seconds to generate a response. With Wikimedia, which is literally a graph database using Blaze Graph, the response and the retrieval of a query is 0.2 seconds, which is extremely fast compared to ChatGPT or Google, and with less resources and less legacy infrastructure, which is also very exciting. So knowledge graphs can provide us more structural representation, and they can reason about the queries and generate reasonable grounded responses. And they are also really good at generating fast responses. Now, we can look at a basic example. How can we use a knowledge graph in uh, in code? For example, like it's a simple code of using how can we use Neo4j. So Neo4j is basically uh, a, a a graph database which is used to store data into graphs. So we will use Neo4j along with LangChain and understand how it can how can we build a basic RAG application with it. So first of all, you just import your again, I'm not doing live demos because I'm actually scared of doing live demos. For some reason, they always blow up. Okay, so for example, you import LangChain, and uh, you have this Neo4j graph. So Neo4j graph is basically a wrapper around Neo4j Python library to be used. So we can use the methods and the classes uh, from Neo4j graph from graph Neo4j library in LangChain. Then you basically create your LLM with the ChatGPT OpenAI class. You pass the API keys, you use ChatGPT embedding model, and that's how you basically connect to your data source, which is actually Neo4j in our case. And this data is basically movie recommendation database. So it's openly available. You can look at it. I'll put it in the resources, and you can explore how it is represented. So you store the entire graph in the memory, and then you create um, a vector representation of it. Once you do that, you create your retrieval chain by passing the vector store, and then you prepare for invoking the response. So you query it, a movie where a mission to the moon goes wrong, and an LLM looks for the information uh, in the graph store if it doesn't already know the answer, and gives you the response. And what you can print the response is like the movie where a mission to the Mars goes wrong is one movie where it's called Space Odyssey. So this is a basic example of how can you use um, a Neo4j graph database as a RAG solution with LangChain. So moving back, moving back to generating now, this is even more fascinating. So every time you query an LLM and you generate response, most of the time it doesn't always come with the same response. It always generates different kind of responses, and you can't really reason about those responses. So there's another way you can actually use knowledge graphs to generate consistent responses. And the other way to generate consistent responses with is by generating ciphers. So what is a cipher again? So with Neo4j, a cipher is like a way to do CRUD operations on a graph a database. So for example, in SQL, you can write SQL queries to get the retrieval from the database. In Neo4j, you can write Cipher queries to query a knowledge graph and access the information. So it's a multiple way technique to generate more grounded responses. So we tried to use Neo4j with RAG, so simply appending the data store and allow LLM to generate the answer by looking at the vector store. Now this is a different approach. The different approach is basically now we're going to use LLM to generate the Cipher query, and then the Cipher query is going to be used to actually provide us the answer. So the Cipher query is going to query the graph database, and it will generate us the answer. Why do we do that? It's because the major benefit is LLMs generating a Cipher statement to answer user questions on. It can generate user questions on the fly and enhancing the responsiveness and accuracy of specific information which exist in the knowledge graph already. So we can look at an example of generating Cipher query with LLM. So again, you do the imports. The imports are literally the same. The one thing that changed here is prompt template. Now we're going to pass a prompt template here that is going to go to the query. So prompt template is basically is a way of putting the template to the prompt that goes to LLM. So the basic steps are literally same. You create an LLM, you connect to the graph database, and then you write a Cipher generation template. Here, you say you're an expert Neo4j developer translating user questions into Cipher to answer questions about movies, convert user questions based on the schema. So now you create your prompt, you create your prompt, and then you pass that to the to the to the chain. And once you have the chain, you can invoke and you can ask the question, what is the plot of the movie Toy Story? And it generates you the cipher. And uh, it, and if you see, the cipher here is literally match movie M with the title Toy Story, return m.plot. Now this cipher is actually like SQL for Neo4j graph database. So by here, I'm saying match the movie, and the title of the movie is Toy Story, and it's going to return me the movie with the title. And since that is the entire object, which is the movie M, I can use a dot and plot to get the property of the movie, which is plot. So the plot is basically returns you the answer. A cowboy doll is profoundly threatened and jealous when new spaceman figures supplements him as a top toy in the boys' room. Okay, but again, sometimes when you do this template, uh, it's not always going to it's not always going to create you the best query, because the LLM doesn't really know about the relation that exists in the Neo4j or in our knowledge graph. So it doesn't know the entities, it doesn't know the relation, so it doesn't really know what's in the knowledge graph. So it tries to create a cipher based on little understanding of whatever the LLM knows. So how do we control and get more predictable and correct responses in terms of cipher? To do that, we can improve our templates. So basically, which leads us to the next slide, which is how do we fix this cipher generation? Sometimes the cipher is not reliable. Sometimes when you query it again, it generates some different cipher, and it could lead to inconsistencies. um, uh, okay, so how do you fix that? So to fix that, there are two ways. You can pass multiple instructions to to the to the template which we used in the code, or you can use something called few shot prompting, where you also give the example which give the example of a cipher so that it knows what the structure of knowledge graph is. So we'll first look at the example for the template instructions. So we'll try to fix the template itself by oops. Uh, okay, so we will look at the template. So if you look at the initial template, you see that this was our initial template. Now, what we're doing is we are passing multiple instructions, and we are trying to control the generation of cipher so it's more aligned and more consistent and more correct. So we are saying use only provided relationship types and properties in the schema. Do not use any other relationship types or properties that are not provided. So with this, we're trying to control the way um, the cipher is generated. So we are saying, okay, just look at the relation that exists in the knowledge graph and only use those. So by doing that, we are basically again doing the same thing, and we are asking who acted in the movie Matrix and what roles did they play. So it generates us again another cipher, and the cipher is basically match movie M, match M movie, where M dot title is Matrix, the uh, match actor acted in. Now this thing R acted in is relation. So actor is related to movie with the relation acted in. So this is the syntax of a cipher in Neo4j. So I'm not really sure if how many of you guys are aware, but let's imagine if there's one person, let's imagine a knowledge graph of Facebook, for example. One node could be me, one node could be my dad. How am I related to my dad? I am the son of my dad. So in that case, I would be a dot person related to S dot son of. So you can name your relation anything. It's okay to pick the names. You can pick names however you want. But once you pick your name, that's your relation to from one node to another node. So here, the actor is basically acted in the movie M. And now, once it retrieves the actor, I'm saying, give me the property name and the role, and then it generates the answer, which is Keanu Reeves and whatever the response is. Now, this is one example. You're basically providing more instructions and trying to control the generation of the cipher and the output. The another example of this um, would be a few shot. The few shot is where you go one step ahead, even one more step, and you actually give it an example of the structure of the knowledge graph. And you say, find movie and genre. So match movie M in genre G and return me the title and and the genre name. Okay. So you now the LLM knows more about the structure of the knowledge graph, and it's gonna stick to the rules of the game. So now, why movie has okay, the query again is what movie has Tom Hanks directed, and what are the genres, right? It again generates the response as cipher, and the result. So match actor, and the name of the actor is Tom Hanks, directed in movie in genre G. And here you see there's a bunch of relations. So the actor is the actor is related to movie, and you see there's a direction arrow here, which is basically trying to say that actor is directed in the movie, and the movie is related to genre. So it's always going in this direction. If genre was related to movie, then the direction would be the different way. Okay. And then return the title and the name, and it returns us the thing, the answer. Okay. So the by using and by generating LLMs, sorry, by using knowledge graphs and using knowledge graphs to generate the answers using the LLMs, we are trying to increase the groundedness of a response, the reliability of a response, because we already have the knowledge and the information about those things in the graph database. So it's more reliable and it's more consistent, uh, in a way. Now, moving on to last few slides, which leads to the future of all of this, which is something I'm still exploring, and it's very interesting. So there's a new project by Neo4j, which is basically NALLM, and NALLM is basically using knowledge graphs using LLMs to generate knowledge graphs from unstructured data. So right now we are using RAGs. Basically, we have vector stores, and we are using LLMs to generate the answers. But in future, there's so much unstructured data on internet, and in there's so much data which is offline, online, and it's all unstructured, but it doesn't have any representation. It has no semantic meaning. And we are using LLMs now to basically generate knowledge from all that unstructured data. So the project basically does what it does is it uses a LLM to extract nodes and relationships um, from the unstructured data, and then we can use LLM again, uh, and use those knowledge graphs to generate more consistent and reliable responses. Now, this is a demo project, and it's very interesting. Now, this leads to something even bigger, which is the next thing, um, which is called graph rag. Now, I'm not sure how many of you have heard of it. It's a project by Microsoft, and it's literally marketed as unlocking LLM discovery on narrative private data. So basically, let's imagine you have a private data set which is unstructured. There's no meaning to it, and the baseline RAG is basically like, use a private data set, chunk it up, store it in a vector DB, and use LLM to do the nearest neighbor and find the response. Now, how GraphRag is different is basically it uses LLM to generate a knowledge graph, and not even generate a knowledge graph, it generate knowledge graph with rich meaning. So you can even do like multi-layer representation of a knowledge graph. So you can reason about every single entity of the knowledge graph and use LLM over and over again to generate more rich knowledge and understanding of the entire data. And then we can use that knowledge graph to again generate grounded responses and more reliable responses. So it's a very good project to explore. And I have seen extremely positive result of using GraphRag and reducing hallucinations and providing more rich and consistent responses with the user queries. Um, that Now that sums up GraphRag. Uh, Now I'm a bit excited about the future of all of this using knowledge graph. So I think knowledge graphs in general are not just used for RAG. I think they are used at every single step of the pipeline. They are used in development of knowledge graph, analysis, deployment, usage, evaluation. So knowledge graph is not just something that you append in your LLM, build the RAG pipeline, um, and look in the knowledge graph. It could be used to improve the efficiency of the retrieval. So it's something that to be researched on, and it's basically like a multi-layer problem to solve, like using LLMs at multiple steps to generate knowledge and analyze the knowledge, generate semantic understanding of that knowledge, and use LLMs in multiple levels of the entire process, not just producing the response at the end. And that basically kind of sums up my talk.